Welcome to Innovate and React. Today's episode will be about how we can turn waste into fuel to defossilize mobility and transportation. I'm very happy to have Theresa Köffler as my guest today because she's working on a demonstration plan for this technology at BEST in Vienna. So you are the first guest which is not based in Germany actually. Welcome, Theresa.
Thank you very much for having me here in your podcast. I'm very honored to be here. And I was really flattered when I got your message and request for this podcast episode. So yes, I'm from Austria. I'm also originally from Austria, from the southern part of Austria. And I'm currently working at the Syngas platform Vienna at BEST. As you already have explained, it's a research company with the full name Bioenergy and Sustainable Technologies.
Mm-hmm. And as I understood, you are coming from the university basically, or the company is founded from the university? Or how did this company start?
Yeah, so the company BEST in Long Bioenergy and Sustainable Technologies began its journey in 2003 under the name Austrian Bioenergy Center ABC as Austria's first competence center for thermal biomass utilization. In 2008, it was renamed to Bioenergy 2020 Plus. So we have had quite a few name changes within our journey. And finally, in 2019, the company adopted its current name, BEST. And we are now aiming on being the link between research and industrial application to strengthen Austria's scientific and technological foundation in biomass conversion.
Mm-hmm.
And BEST does that via like applied R&D focused on biorefinery processes to develop and demonstrate thermochemical syngas conversion technologies. So that is basically our research focus on the conversion of biomasses. In our company, there are also several other areas that are doing research in other fields like automation and control, or we also have another research group that is looking into the sustainability of these processes and looking on the value chains. But my research group is located in Vienna, so the capital of Austria, and the headquarters of our company is situated in Graz, which is the second largest city. And we have around 100 employees at the moment, so we're not like that big, but also not that small.
Yeah, but for research company, I think that's not tiny. Like I know some from the university, they're just a handful of people. So 100 people is already quite big. And you're trying to close the gap between the research from universities and fundamental research to the giant industrial processes, right?
Yes, exactly. So we see ourselves as the bridge between the universities and the industry. So we have like several projects where we have different stakeholders and partners involved. Like we have a lot of different universities, like the Technical University of Vienna, but also the BOKU. That is a different university also based in Vienna that is focusing more on, I would say, the woody biomass research. Like we say, it's the green university here in Vienna. But we also have some cooperations with the university in Graz and also international universities. And we have a lot of industry partners that come to us if they have any like topics that they want to look into in more depth. And we bring all of the stakeholders together and try to create a project that is then also funded by the partners, but also by the national agency, which is called FFG in Austria here. But we're also participating in several European projects where we do different topics and projects throughout Europe. Yes.
Yeah, I think that's a very important work because especially in these newer kind of technologies, it's also for big companies to start their own research on this is a bit hesitant sometimes, because it's a lot of commitment, and when they can cooperate with companies like you and have also parts of the university and government funding into this, it's a lot less commitment, I would say, but still it brings the technology forward, which is then the basis for the future technology.
Yes, exactly. So like we aim on encouraging the industry partners to adopt our technologies and to build these technologies in a larger scale, because we only have pilot and demonstration plans, but for the processes to be economically viable, you have to upscale it a little bit more. And for sure, like these new technologies, they always have some risk involved, and the industry partners, they first want to see that these processes work before they invest in these new technologies. And so they are really willing to cooperate a lot, and we have some really fruitful conversations and projects with them. Yes.
Yeah, great. About the pilot plant and the demonstration plants, we'll be talking later more in depth. But first, how did you get into this company? You studied also in Vienna, and then?
Yes, my academic path, I would say, was not really a straight line, but still it helped shape where I am today. So I started out at a high school with the focus on languages, but there I had a really inspiring and unconventional physics teacher that inspired me to go into the renewable sector, I would say, because he was talking a lot about the climate change, and I said, yeah, okay, that is a huge thing, and I also want to like create an impact and try to help solve this big issue. And then I started to search for a bachelor's degree in that area, and then I found one which was called Environmental System Studies in Graz. And then I did my bachelor, or I started there. And then after 2 semesters, when I like got an overview about the course program, I said, yeah, okay, that's nice. And we get an insight into the various areas like chemistry, physics, also mathematics and so on. But I didn't really know what to do with that. And also I was lacking the aspect of technology in this study program. So I then again had another look and looked at other universities and found at the Technical University of Graz the bachelor program Process Engineering. I found that, and I like looked into the curriculum, and it was exactly what I was looking for. Like, it was a combination of process engineering and also chemistry, with which I thought this would be a good combination to go then into the environmental engineering direction. And so I finished both bachelor degrees, because the other one was also interesting, but I didn't really see my path there. So then I completed my bachelor's in Graz. And,
so you have both bachelors in both fields?
Yes, exactly. Yeah. I would not recommend doing 2 bachelor degrees in parallel, but it's nice. And I also got some valuable insights, because the environmental system studies was really a program where there were a lot of different disciplines, and I got to engage with different students from different areas, so I wouldn't miss that. But I wanted to go more into the technological pathway, so I decided to also study the other one.
It's not completely different from another, right? So it's like knowledge from one of these degrees feeds into the other, so it's not completely useless and you don't have to start from zero.
Yes, no, it is similar, but still studying at the technical university is quite different to the like a non-technical university where I studied before.
How is it different?
How? Yeah, in my opinion, like in Austria at least, especially the first few semesters, you have a lot of fundamental basics that you have to learn, like thermodynamics, the principle of chemistry. Then you have mathematics and the mechanics. You also have in the first few semesters you have to learn like a lot of these issues and also the engineering basics. And at the University of Graz, there we only had like physics, chemistry and mathematics, but we didn't have like any engineering part. And at least for me, the engineering part was quite challenging since I was studying before at a high school with the focus on languages, and I didn't have a clue about any of the engineering stuff, and also how to draw some technical drawings. I didn't have a clue, and in my opinion, also it is also like the professors at the Technical University of Graz, they demand quite a lot already in the first few semesters. So you really have to put the effort into if you want to go on with it and succeed in it. Yeah.
Yeah, I think that's also why most of the engineering courses are not really easy. Like you have to dig into all these new topics that you don't really learn in school that much. And then at some point, everything clicks together, but that takes a while.
Yeah, exactly. For example, like thermodynamics.
Yeah.
I really liked that course, and I have a lot of other colleagues that were really struggling a lot. But for me, like you have to come to the point where it clicks, and you then really understand it, and you can then solve the problems easily because you understand the underlying principles. But to come to that point, that takes some while.
So once you get a solid grasp of the fundamentals, the fun part actually starts. So you get to choose your specialization within the master's program. I specialized in plant and process engineering with a focus on environment and resources. My journey then kicked off with a semester abroad in Bologna, in Italy. It was right in the middle of COVID, which brought its own set of challenges.
Wow.
But despite that,
Yeah, that's a shame.
but since I went there after the first wave in Italy, it was quite enjoyable, and we were able to do also stuff that we couldn't do in Austria at that time. So I had also an amazing time studying and living in such a lively student city.
Great.
After that, I returned to complete my master's at the TU Wien, where I took a course which was taught by Matthias Kuber, who, as it turns out now, is my current boss. That's also when I first heard about BEST, because he presented it to us and we were able to go on a site visit. And I was immediately fascinated by the applied research they were doing there. So soon after, I started my master thesis with them. And well, they haven't gotten rid of me yet. So I'm now in my PhD, doing my PhD there, focusing on Fischer-Tropsch synthesis in a very young, passionate, and highly motivated research group.
Yeah, that sounds great. Talking of the topics, you are now studying the conversion of waste into fuels. And in the last episode of the podcast, we were also talking about energy carriers from CO2 and hydrogen, how we can basically synthesize fuels via the methanol route from CO2 and hydrogen. And from there, you can also produce jet fuels. But in your case, it's the Fischer-Tropsch synthesis. Yeah, this is a relatively old technology. We actually met at the 100-year anniversary conference on Fischer-Tropsch synthesis in Mülheim, where it was discovered. So it's an old technology, but now has a lot of new application possibilities due to the green chemistry research or green energy research. And let's first introduce the Fischer-Tropsch synthesis. What is this reaction?
Okay, yes, so the Fischer-Tropsch synthesis is basically a chemical process that converts carbon monoxide and hydrogen into liquid hydrocarbons of different chain lengths. So this process basically always takes place at elevated pressure, so between 20 to 30 bars, and temperatures between 200 and 350 degrees Celsius. In my case, we are using a slurry bubble column reactor, but you can also use like different reactor configurations, like fixed bed reactors, fluidized bed reactors. There are various different configurations that can be used with this synthesis. And the basis, yes, is quite old. So in the 1920s, it was invented. Even though it is quite old, it has now a revival because we now need sustainable aviation fuels and also sustainable liquid fuels in general. And the advantage of it is that if you change the feedstock, because like earlier it was coal-based or gas-based, to some biomass or also waste streams, then you create like sustainable fuels.
So when the carbon source is different, but the process fundamentally stays the same. When you have a waste stream that is ideally organic waste, then you can also get biofuels out of it because the carbon eventually comes from these organic compounds, right?
Yes, exactly. So in principle, you could just swap the fossil-based feedstocks to non-fossil-based feedstocks and substitute that in order to create some sustainable products out of it. In principle, that is possible to do, and we have also demonstrated it. But the big challenge is that the fossil-based Fischer-Tropsch refineries, they are huge. They have scales of like, I think, a production capacity of 140,000 barrels per day. And because the feedstock deposits or the feedstock storage, they are like massive, and they're concentrated in some areas like South Africa and also other parts of the world.
I think China is also very big in Fischer-Tropsch synthesis, right?
Yeah. They are also quite big. I think there's some big players also in China that I think they're using now also coal, but like they are switching to the gas as well. But yeah, the problem is with swapping the fossil-based feedstocks with non-fossil-based feedstock is that we don't have these huge amounts of non-fossil feedstock that we could put into these refineries. So basically we have to scale it down, the technology and the reactor. And there are not a lot of companies existing that want to scale down because
usually
because
it's always up.
Yeah, exactly. And for example, Sasol is a huge player, and they have like revolutionized the market with their technology, and they are operating quite well, and they are a huge player. And we were talking to them also, and also at the conference I was talking to some colleagues, and they said, yeah, they are just not really interested in scaling down to our size because they have the knowledge now for these huge production capacities, and for them the revenue doesn't lie there. So here we come into play, and we want to develop like these smaller scale facilities that we can feed with biogenic feedstock or also waste material to create these sustainable fuels and also chemicals.
So the problem there is that we just don't have enough of this biogenic waste.
Yes, exactly. Or I mean, like if you would sum it up worldwide, then we would have enough, but they are more evenly distributed than the fossil-based opponents.
So it's more a decentralized approach instead of the centralized approach we have with the big oil and coal refineries. Yeah.
Exactly. So I think like realistic for these decentralized plants would be a size of 2,000 barrels per day, which is significantly smaller than the huge production capacities of the now in industrially operating plants. But if we make it smaller, then there are some advantages that we could get out of it, since we can distribute it like widely. So not only in one country it would be possible to operate it, but in several countries. So it would enable a country to produce their fuels on their own, and they would not rely on other countries.
So they're more independent.
Yeah, exactly. Which is the thing I think every country is now like really looking into, because relying on others in the world like this is maybe not the best idea.
Yeah, we have seen what happened with Russia. And
yes, exactly.
We were basically, that was in Germany especially, I don't know how it's in Austria, but in Germany, all this huge chemical sites we have were kind of reliant on the cheap Russian energy we got. And for example, in Ludwigshafen, the BASF site is giant, and they have their own pipeline basically from Russia to there to obtain all their carbon sources and the energy. And now they have to think about new technologies, and they're investing a lot in also hydrogen, and I think also biogenic starting material to be less dependent on these players. And this is exactly also where this Fischer-Tropsch feeds in. When you have a collection point for waste, and they collect all the green cuttings from trees and whatever, then they could use that to produce fuel.
Yes, exactly. That would be the idea. And it was also in Austria the case that when we saw the crisis with Russia, that we had a lot of issues. But that was also a starting point for new technologies and also new initiatives from the industry, because they really wanted to like change, and they had to change. So that was great, I think, in that perspective, that now we talk more about that. But these technologies is now new. So like using sustainable feedstocks for the Fischer-Tropsch synthesis, I think like we are trying to do that only like since 10 to 20 years now. And this has some huge challenges connected with the syngas production. So maybe I could explain first what syngas is.
Yeah, that would be great.
Because I think our audience may not know this term, but for us it is a term that we use every day. So synthesis gas is mainly a mixture of CO and hydrogen with like, it can also contain some CO2 and methane, but the majority of it is hydrogen and carbon monoxide. And we call it syngas because it is utilized to synthesize other chemicals and fuels, and therefore the abbreviation syngas.
Yeah. So the basis for a lot of other chemical processes.
Yes.
And
yes, exactly.
How do you get the syngas out of the biomass?
Via thermochemical conversion. So, for example, in our case, at our research plant in Vienna, we use our dual fluidized bed gasification. So it's basically a thermochemical process where we just put in, for example, woody biomass or some sewage sludge, or we also have tried to use coconut shells or also cashew shells. So like whatever our partners give us, we feed it to our gasifier, and there we have temperatures between 900 to 1000 and like 1200 degrees Celsius. And in that atmosphere, with the addition of steam, we then generate this synthesis gas that we then have to clean in order to use it for the Fischer-Tropsch synthesis. And especially this cleaning step is really crucial for the utilization of this gas then for the next synthesis steps. because the catalysts used in Fischer-Tropsch synthesis.
What catalysts are these?
Yeah, we mainly use cobalt-based catalysts on alumina oxide basis. But there are also in the industry iron-based catalysts used. This depends on the product that you want to obtain. If you want to obtain like more waxes and more diesel range products, then you most of the time use cobalt-based catalysts.
With the cobalt, you get longer chain length than iron?
Yes.
Okay.
Yes, exactly. And for example, also iron-based catalysts are mainly used for the application in high temperature Fischer-Tropsch synthesis, so temperatures between 250 and 350 degrees Celsius. And since iron is also water gas shift active, you can also feed carbon dioxide, and then the iron catalyst can convert it into CO and hydrogen. And this would also be possible. So it could also be an option to feed CO2 directly from like different carbon dioxide sources and feed it to the reactor. Yeah.
When you have the synthesis gas production, you get a lot of side products, and these side products might harm the catalyst and would deactivate then the synthesis. What are the side products you want to avoid, that you want to get out? I mean, ideally you want to only have CO and hydrogen, but I assume there are also some.
Yeah, there are various side products that we don't want to have. For example, tars. We want to get rid of them, and we do that by using some rapeseed methyl ester or like biodiesel scrubbers. We use them at higher temperatures, and then we also have a low temperature scrubber to get rid of them. Then the syngas also includes some soot particles that we get rid in cyclones. And the most important thing is to get rid of some sulfur components that would definitely harm the catalyst and would deactivate it and poison it. And that we get rid within the activated carbon beds that we have. And also ammonia is also not good for the catalyst. So for that we use some water scrubbers. And I think that is the most important thing that we have to get rid of. Yeah.
And with this clean synthesis gas, you then go into the Fischer-Tropsch reactor. And then I assume, because the synthesis is not very selective for one chain length, you have to do some downstream processing as well, right?
Yes, exactly. So maybe I can give you an insight into our plant setup. So we are using this slurry bubble column technology. I mean, this is a weird word, and I think not a lot of you know what it is. So I'm just going to give you an insight briefly. So basically, you can imagine it as being a cylinder filled with some wax in a liquid state at these process conditions. And the syngas is entering the reactor at the bottom via a sintered plate, which is just a plate with really small holes in it. And then the catalyst is suspended within the liquid, and the syngas then reacts with this catalyst and forms also like different hydrocarbon chains in different lengths, and then the product is being removed at the top of the reactor via some filters to avoid that the catalyst is also like being washed out of the system, and to retain it in the reactor.
So it's getting out there in liquid form.
Yeah, liquid and gas form. I would be really curious how it looks, because in our plants we cannot have a look inside, since we already have like some, like our reactor itself has height of 3 meters and a diameter of 30 centimeters, and it's made of steel, so we cannot have a look inside. That would be really cool if it would be glass or something like that, so that you could see.
A window.
But yeah, But basically it enters in a liquid and gas state, and then we have to condensate the product, and we do it by lowering the temperature according to the desired fractions we want to get. So, for example, the waxes, these are the longer chain hydrocarbons, they condensate at higher temperatures than the naphtha fraction, for example, which is the fraction between C4 and C8, for example. So we then apply a three-stage thermal condensation process. It is basically just we have some heat exchangers at different temperatures and some vessels, and there then the product condensates, and the remaining gas then flows to the next condenser at the lower temperature, and so on. So it is a three-stage condensation, and then we get the product of the three stages. So we have some wax in the first stage, then we have the diesel fraction in the middle, and the naphtha fraction in the third condenser. And if we then want to use it as a, for example, substitute for diesel, we have to refine it further.
So you get three crude products basically. Do you also
Yes.
get a gas fraction that you can feed back into the reactor, or is it completely used up?
Yes, that's true. We also have remaining gas that is not converted, and also there is some methane that is formed, which doesn't condense at these temperatures that we have. So we also cycle this remaining tail gas, we name it, back to the reactor to enhance the overall conversion of the process. Yeah.
Interesting. So also the methane can go back in the reactor, and it will then start or will attach to another chain that it becomes longer, or is the methane just cycling around?
Yeah, unfortunately, the methane is like cycling just around and just increasing over time. It would be great if we would have a steam reformer in the tail gas loop so that we could reform the methane to hydrogen and carbon monoxide. But in our process configuration, we don't have that since we are quite small and it is quite expensive, these kind of steam reformers. But we are looking into it. But
So for a
in bigger
larger
plants,
plant, that might be a viable option.
yeah, you definitely have to do that. Yeah,
Okay.
you definitely need that. Yes, exactly. And so if you want to use then the waxes and the chemicals that have been produced, you definitely need some downstream processing. You need some hydrocracking for the waxes in order to get the jet fuel range, which is in the chain length range of C8 to C16, I think. And then also we need some isomerization processes to improve the cold flow properties of the fuel. Yeah, but like I think there are also several other necessary steps maybe, but that's not my research area, so I cannot give you that much insight into this.
But you get the jet fuel out of the wax part.
And the diesel freight, yeah.
Okay.
It is
Both.
always a mixture. So I think if you give then the wax and the diesel to a refinery partner, for example, they then hydrocrack the wax, and then they also mix some diesel fraction into this mixture to produce the desired chain lengths.
Because the hydrocracking yields similar chain length than the diesel, or longer.
Yes. No, you can basically decide via the process conditions which chain lengths you want to get out of the hydrocracker.
And then the third fraction, the light fraction, that can be used to synthesize chemicals, or what do you do with this?
Yeah, I would say you could use that for some base chemicals. You since they are like a smaller chain, you can try to even like crack it more so that you get ethane or something like that. Yeah, I would say like base chemicals you can make out of that.
Yeah, so you could also not just transform the fuel production, but also the chemical production with this, because it's so low in the value chain that it basically is the beginning for a new kind of synthesis. Interesting.
Yeah, exactly. Yeah, there is a quite huge variety of products that you could synthesize with this process.
Yeah, but I guess it's also for the chemistry to have a steam cracker that is competitive to the current steam crackers, and you would also need very large quantities. So maybe also a thing for the future, but yeah, it might get there.
Yeah, I think we have to adapt our current setups also in the refinery processes that can handle these smaller scales, I would say. So we just have like the chemical engineers and the chemists, they just have to work together and find new solutions for the smaller scale productions. Because if you just want to substitute the fossil-based feedstocks and then put like really small quantities into existing infrastructure, I think that will not be profitable.
But do you think it could be possible to have such a small plant, for example, near a fueling station at the Autobahn, and then you basically produce all the fuel you need for this fueling station on site?
So I mean, this idea is not that abstract, I would say, because actually we have now a project where we want to scale our technology up, and this would happen, I think, in Styria, so in the middle part of Austria. And there, in the project plan, we also want to build a refining part of the Syncrude we call our FT product in the size of a container. So we actually want to do that we also can refine the product directly beside the existing plant.
Inside a container, that seems challenging, because usually when I imagine a refinery, they have all these 20-meter columns for the refractive distillation and stuff like that.
Yeah, I'm also really curious how they are going to design that, but we will hopefully see that it is also possible on a smaller scale.
Yeah, but maybe also at this scale, other technologies than distillation might work. Who knows?
Yeah. I think it is possible, but that's not my research topic, so I cannot dig into that.
But then for the plant you are building now, you told me before that you started with some parts of it, and then you are now fitting all the parts together. So your approach is now to actually go from the waste to the final product.
Yes.
And what is the main challenge in doing that? I think each process step on its own is much easier than combining them all together, right? So what are the challenges in combining them?
Yeah, the challenge is, for example, the feedstock variability. So, like, if you get one container of wood chips, this container can deviate from another container that you get. So it is quite difficult to predict the syngas composition. And for the Fischer-Tropsch synthesis, for example, the H2CO ratio is really important. So it should be around 2. And so the gasification section should provide the syngas with that composition. But if the feedstock varies, then there are some deviations from this optimal composition. And so I think the most important or difficult part is to keep the gasifier running with our desired syngas range. And another thing is, if you then use more challenging feedstocks like sewage sludge, or also like we have tried to use a mixture of wood chips and plastics, then you get like quite challenging contaminations within the gas. You get more sulfur components and also some ammonia components that are not desirable within the syngas. So you have to adapt the syngas cleaning part. And this is a part, like the syngas cleaning, is a research area that not a lot of researchers have focused on, since we only have always looked at the syngas production and then the use of the syngas within the reactor, but the bridge between it, the syngas cleaning, this is a topic that no one was like thought about it, because we have a professor, for example, that revolutionized the gasification part, because we have a like advanced gasification technology, and the Fischer-Tropsch part is also like state of the art, but the cleaning of the gas, that is quite challenging. So we are now looking into how to modify the gas cleaning depending on the feedstock we are using.
Is it a fixed process, or can you have some modular concepts where you, I don't know, have some, the feedstock is wood chips, and then okay, usually we have only these contaminations and you don't need process step X. And when you put also plastic into the mix, then you definitely need also this other process step. Or is it one big thing?
Yeah, so in our current setup, and I also think that in industrially applied processes, there will be no like modular gas cleaning steps. I think there will be like the gas cleaning should be possible to clean the gas with the worst, I would say, feed gas source. And I think that is also a really important point that we have to keep in mind for the adoption of this technology. And the bigger plants should focus on one feedstock and like optimize this gas cleaning, and then also downstream the Fischer-Tropsch process. And another one should focus, for example, on using plastic fractions, because then I think that's easier also for the gasification part, because it is way easier to gasify woody biomass than some plastic fractions, because they have like way more tars and it is way more complicated, or complex. So I think the plant should like only use one specific feedstock and then adopt on required cleaning steps.
So like traditional oil refineries, which process mainly one kind of oil, for example, from the North Sea, and have specialized exactly to that impurities that come from this source.
Yeah, I think that's the easier approach, because our gasification plant can also like deal with the more challenging feedstocks, but we see if we use them that we have like way more issues during the operation. I mean, it is possible, and you can just adapt the gasification part by like changing some screws or like conveyor belts and make them more resilient to these feedstocks. But I think it is easier if you operate a plant always with the same feedstock. But in our case, we want to demonstrate the use of different feedstocks to some industrial partners, and therefore our plant is capable of operating nearly everything. But I think when you want to build a bigger plant in the size of some megawatts, then you definitely should focus on one feedstock.
So that is how you bridge the gap from research to industry, because in this way you show which kind of purification works and which not, and then the industry partners can adopt that technology for their plants and go to a bigger scale.
Yeah, exactly. Because our gasifier, for example, has a input capacity of 1 megawatt, and I think like industrial plants should be in the range of at least 10 to 50 megawatts, so really bigger, like a huge step then towards the next generation. And our Fischer-Tropsch part only uses 250 kilowatts of this syngas that is being produced, since we have used the reactor that was already existing, and this reactor was commissioned at another facility. So we are limited with that, and now we are looking just in the coupling of the two plants.
The next step would be to scale up this whole plant, since you have shown that each separate parts of the plant work on their own. Now you have connected them, so the next step would be scale up. But this is then done by the industry partners who pick up your technology and use it on a larger scale, right?
So basically our process design already works in our scale, and I think also this process steps involved and also the different reactors and plant units. If you want to build a bigger one, then I think you can just build up on that, and we have already designed some bigger plants with our technology, so this is definitely possible, but the industry partners, they are resistant because it is really new and not a lot of companies have these technologies. They are hesitant to enter this market, but basically it would work with our technology, and we have shown it in several campaigns that we can convert sustainable feedstocks into SAF, so sustainable aviation fuels. Yeah, but you need the courage.
Yeah, I think with really big companies, it's always a problem to adopt new technologies because it might fail. It is not an established technology, so they have to think about doing their own research or not. And this is really great that there are companies like BEST where you can support this transition from research into the industry.
Yeah, so that is our aim, to like help our industry partners to adopt this technology for their markets and for their projects. So we don't have patents or anything like that. So our interest is on bringing this process further and producing sustainable chemicals.
And there the Fischer-Tropsch process really has potential, and also for jet fuels alone from the quota that will be coming from the EU regulation. This will drive demand, and then we need these production capacities to keep up.
Yes, exactly. I mean, there are different paths to substitute the jet fuels, but the Fischer-Tropsch synthesis part is already ASTM approved, so this fuel regulation, and I think like the European Union wants to decarbonize in the near future already, like the aviation sector, quite rapidly. And right now, the current mix that is possible to use our Fischer-Tropsch fuel in the aviation sector is 50%. So you can like mix the fossil-based fuel with 50% of the renewable fuels, and there are already some aircrafts and airplanes that are flying with this sustainable aviation fuel. So it is working, and it is also quite clean, the product that we give, because it lacks of aromatics and other components that are not that favorable. But yeah, the demand is really huge, and so I also think that in the near future there will be, and they have to be, more Fischer-Tropsch plants using renewable biomass or other feedstock sources. But nevertheless, I think it will be a mixture, because there are also different routes with which we can produce sustainable fuels. I think we have to adopt all these technologies in order to substitute now the fossil fuels and to reach the ambitious goal of the European Union.
Other feedstock could also be CO2, right? And then use CO2 and hydrogen to make synthesis gas, and then use this in the Fischer-Tropsch synthesis?
This is a quite hot topic. We have seen a lot of different conference contributions to that at the conference where we met. And also a colleague of mine who recently joined the company is looking into exactly this path to use CO2 directly by using iron-based catalysts. That is a hot topic, but in my opinion, if you use CO2 instead of CO, then you have an additional conversion step. So you have to convert first CO2 into CO, and that makes the whole process more inefficient, I would say. So I see that there is going to be a lot of research, but on the short term, I think the coal-based catalysts are still more efficient than the iron-based ones.
Yeah, we probably need all the solutions we have. It's not just the CO2. We also need to convert the waste and use that. And the Fischer-Tropsch synthesis combined with your gasification technology would be a great option.
Yes, exactly. So I think that the Fischer-Tropsch synthesis is a really good solution to that, or also contribution to this issue that we're facing. And the thing is now only that we have to build the plants, and that the industry really adopts our research and technologies. And we have seen at the conference that various research groups are working on this topic, and it is still, nevertheless, it is already 100 years old. There is huge interest in further optimizing the synthesis and understanding the underlying principles to use alternative feedstocks.
Also, in combination with electrolyzers, this technology can be used to turn electricity into liquid fuels, which is a very powerful option, I think. For example, if we use surplus electricity that we cannot use otherwise, we could store it into jet fuel and then use that for aviation, where we have currently no other option than liquid fuels.
Yeah, I really see the adoption of the power to liquid processes coming up. So within this technology, you use electric energy and a carbon source, ideally CO2, and then you can synthesize the Fischer-Tropsch products only by using CO2 and energy to synthesize then the necessary syngas. And we have now already a project in that direction. So there is going to be another plant, electrolyzer, that will supply different syngas then, because we see here also a huge potential, and there are also a lot of industries that are now going into the direction of the electrolyzers.
You mean the co-electrolyzer, where you use CO2 directly?
Yes, exactly.
Yeah, this is a really fascinating technology where you can basically use water and CO2 directly to get hydrogen and CO, which is syngas in one step instead of separate step where we have first the water electrolysis and then the water gas shift reaction, and then you have your syngas. And with this, it's much more efficient.
Mm-hmm, exactly. That is the exact technology that we are going to build at our demonstration plant here in Vienna. And if that project works out, then this would be really huge, because I think no one has ever built a co-electrolysis plant that size. But therefore, I really am looking forward to this project, and I really hope that it's going to be a success, because with that, I think we would have already demonstrated 2 different pathways to produce sustainable fuels.
The more, the better, I guess. This is great then for becoming more independent from energy imports, and we can use our own electricity and the bio waste we have to produce these fuels?
I mean, one question that I always ask myself if we have these power to liquid concepts is, do we really or are we really able to produce that much of electricity that we have it like in surplus? And then also, is this surplus energy really going to be that cheap that we can operate these plants? But in principle, this would be really a nice pathway also to produce these Fischer-Tropsch fuels.
A lot of this will also depend on the regulations and what incentives there will be to build such plants and actually use the renewable energy.
Yeah, and also like if the government then gives some or sets some incentives for like producers and manufacturers to use these technologies so that they get, like, for example, if you get additional money, if you have like some carbon neutral technologies, then I think then the industries would even be faster at adopting these technologies. But I don't know how it is in Germany, but in Austria, for example, we were like, I think 2 years ago at the point, or also like 1 year ago, I can't remember, when there should have been a new regulation that would have like really pushed it forward, because 2 years ago we still had the Green Party in our government, but unfortunately this never came, and then also a lot of these quite innovative projects were cancelled because the industry then said, yeah, okay, if there is no incentive from the government and no insurance that they get a certain price for their product, then they just like the risk of building these plants is too high. I think the government plays a huge role for the development of these quite new technologies.
Yeah, definitely. As long as the fossil alternatives remain that cheap, the motivation is just not big enough to commit to this renewable energies, because why should I invest in the green technology if others can make much more money with the fossil fuels? And also for the electricity grid, the more wind and solar we will integrate into the grid, the more surplus energy we will have, and this surplus energy could be also used by co-electrolyzers and then make liquid fuels for jet fuel, for example, that we have to produce anyway.
Yeah, exactly. This would be ideal if we could just then switch on our FT plants and just use the electricity within the co-electrolyzers to produce some renewable fuels. That would be ideal. I totally agree with you on that topic.
Great. Thank you very much, Theresa, for taking the time to share your research, talk with me about the Fischer-Tropsch process, which is truly fascinating. Thank you very much.
Yeah, thank you very, very much for having me here. It was a pleasure to explain my research a little bit and to talk with you in a really nice environment.
Also, thank you very much for listening and spending the time with us. If you liked this episode, please hit the follow button and give this episode a review. This really helps the show more than you think. If you want to read more about the research at BEST, the links will be in the show notes. And if you have an interesting topic to discuss in the podcast, then send me an email to contact@innovateandreact.com or find me on LinkedIn. Until next time, keep innovating and stay curious.